hear us well, can see the presentation. We're going to wait some seconds for everybody can connect. If you have any technical issue, do not hesitate to write it down on the chat. Gwen and Clementine, which are backstage today, will do the best to resolve this issue. It's also the occasion for me to thank them for helping us to prepare and to organize this webinar. So now if everybody, I think now everybody is well connected, we can get started with our presentation. So hi everyone, I'm Julien Bayol, I'm Assistant Product Manager at Cailabs. And today we'll be discussing about how Cailabs answered the need of a company, Coriolis Composites, which is specialized in automated fiber placement by designing an ultra-compact beam shaping laser head that is called CANUNDA-HP top-hat shaper. To do so, I'm very glad to host Denis Cartier, which is Composite Development Manager at Coriolis Composites. Hello, Denis. How are you today?
Hello, everybody. Hello, Julien. I'm very well, thank you. Thank you for the invitation to participate to that webinar. I'm very pleased to be talking to everybody right now.
Okay, thank you, Denis. Shared pleasure. So, to give you an idea of the path that we'll be following through this webinar, here is a short slide. So first of all, we think that it's important to define what is the process, what is automated fiber placement, and actually who can do it better than Denis, which is a specialist of this process. Thanks to this short introduction by Denis, we will have a better idea of what makes a laser head, a beam shaping laser head, suitable for the IFP process, and what are the integration constraints to integrate it into an IFP machine. Afterwards, we will be discussing about the results. First, on the optical point of view, we describe the beam shaping solution that has been developed by Cailabs, discussing the optical performances of this laser head, and also explaining why the core technology of Cailabs, the MPLC, is particularly suitable to answer the Coriolis Composites needs. Then Denis will discuss about the integration and process results on a Coriolis Composites machine. And then we'll be discussing about what will be the next steps for this laser head called CANUNDA-HP top-hat shaper. So it's the question for me to tell you, if you have any question, please write it down on the chat. I think the Q&A mode is activated, so we will have a moment at the end of the presentation to answer to any question you may have. Before we go more in detail in our presentation, a few words about our company. I promise I will be as concise as possible and to get to the point quickly. So Cailabs is exploiting a unique technology called the MPLC for multiplane light conversion, and have a strong expertise in beam shaping and optics. Thanks to that, 19 patent families have been filed, and our activity is at 70% at export, thanks to more than 20 sales partners around the world. So to sum up what we do at Cailabs, we like to say this sentence: we develop, thanks to the MPLC, manufacture in-house and sell innovative optical components. Few figures about the company. We have now 60 employees, including 1/3 of PhDs, and we have raised almost 17 million euros. So as I said earlier, the MPLC technology is really at the core of the activity of Cailabs. So this activity is divided in 4 main product lines. The first one is called Aruna, and aims at increasing the throughput of fibered local networks. Then we also have Proteus, which is more laboratory dedicated product line, which provide multiplexing solutions, and that the objective to invent the optical networks of the future. Then we have also TILBA, which is devoted to ensure the reliability of free space optics communications with, for example, atmospheric turbulences mitigation solutions to improve, for example, space-to-ground laser communication links. And then, last but not least, we have the product line that will be focused on today, which is CANUNDA, and that aims at improving laser material processing. More in detail, we'll be discussing on the universe of CANUNDA of precisely the CANUNDA-HP products. HP standing for high power, which are actually beam shaping laser heads for multi-kilowatt lasers dedicated to macro processing applications. So those applications, we have some, let's say, conventional laser application, such as laser cutting, drilling, or welding, but also newer application. For example, additive manufacturing. Here in the on the picture, you can see on the left direct energy deposition process, and here selective laser melting. But also composite heating that we'll be discussing more in detail today, or laser texturing or cleaning. All those applications can be applied to several markets, for example, automotive, aerospace, naval, or diverse machines for industry. So it's now time to go more in detail in our subject of today. And even if some of you in the audience may already know what is IFP, I think it's important to define it. And so, Denis, I ask you the question, what is automated fiber placement and what do you do at Coriolis Composites on this process?
Thank you, Julien. So what is composite fiber? What is automated fiber placement? Well, first of all, I will do a quick introduction of Coriolis Composites. I can see in the people who are connected that a few of us know us, but Coriolis Composite is it's a small and medium company which is specialized in the development and supply of robotic system for the automation of the manufacturing of composite parts. In the Coriolis group, we use two main technologies, one is automated fiber placement, which we'll be detailing a bit more later on. And the second one is filament winding, which is a technology which is more used for pipes or reservoirs, for example. The Coriolis Composite Coriolis is a French independent company founded in 2001, and we have about 150 machines installed worldwide. That's for Coriolis and MF Tech. And the company is about 100 persons now. So what is automated fiber placement? So rather than doing lots of text, I've put a few pictures of machines we have. Automated fiber placement is the manufacture of composite parts by lamination of layers of composite material onto a mold. To do that, we use a robot, which has a head, which is rolling onto the mold. The material is stored into a creel at the back of a robot, and is fed through to the head using pipes. It's what characterizes Coriolis machines. On the pictures you can see here, I hope you can see my mouse, you can see a deposition head there, manufacturing a composite thermoplastic parts into a curved tool. And so that's really the essence of composite fiber, of automated fiber placement. We come in contact into the tool with a robot head moving and depositing the composite materials into the tool. So now a bit more in detail into processing thermoplastic materials in the technology using the automated fiber placement machines. So as I mentioned before, to manufacture parts, we know the head is gonna roll onto the surface of a tool. And on the one hand, we have tapes which are fed into a tube into the deposition head. On the roller here, which is at the base of the head, which is rolling on the surface and applying pressure on the surface. For people who know composite materials, thermoplastics are solid at room temperature. So in order to make the plies to stick on top of each other, you will need to heat the material and reach the melting point of the resin so that the two plies are welded together. So on the picture on the right, you can see a bit better the tape which is being fed through a guide, and then the roller applying pressure on the surface. And in order to control the process, we heat the material with a laser beam, or control with high power laser beam. As you can see in the picture, we need to reach a melting temperature or above melting temperature of the composite, which is on the order of 400 degrees C. And in the case of fast layup, this 400 degrees C needs to be achieved while the head moves at speeds up to 1.2 meters per second. So the heat, a lot of heat is brought to the material, the tape being fed on the substrate using that laser beam. Our controlling parameters are the height of the laser beam, its incident angle, on the repartition of the laser beam on the substrate on the material being deposited. So that in a few words, summarize the thermoplastic processing of automated fiber placement.
Thank you, Denis, for this insightful introduction. I think now we can better understand in what consists automated fiber placement, particularly what is important for the heating systems that have to be integrated on those machines. And this is the context in which Coriolis Composites asked Cailabs to design a high-quality beam shaper to be integrated on the IFP machine to heat the composites. So it's time now for the first survey session of this webinar. So we will make you participate a bit more in this webinar. So we would like to know, according to you, what is the most important laser beam shape parameter in the IFP context? So you can scroll down on your screen to select what you think is the most important parameter in the IFP. Maybe it's the plateau homogeneity in terms of laser shape intensity, maybe the dimensional accuracy of the shape, or maybe the sharpness or the depth of field, or maybe another parameter. Please feel free to write it down on the chat if you think it's another parameter. So I don't know if everybody has voted, not yet. So I think that you can speak only one answer. So we're gonna wait a few seconds more to let you have the time to make your decision. I know it's not an easy question. Maybe you are more or less familiar with the process. So if you're not, trust your feeling about that. So we are about 55% of the people that have been answering. 64%, sorry. Few seconds more. Okay. So now I will stop the survey. So now we can see the results. In the same way, to pick the answer, you can scroll down to see the results. So we can see that for you, majority think that the plateau homogeneity is more important than the other parameters. And two of you think it's another parameter. So as I said, feel free to write it down on the chat. We'll be interested in know what you think by other. So so now we're gonna go back to the slides. So here it is. So yes, this survey was to give you an idea of how we can understand the needs of Coriolis Composites and how we can build a bit of specification from these needs. So as I presented, there is in fact, yes, an optical challenge, but at Cailabs, we also saw, and while discussing with Coriolis Composites, we saw actually two main challenges. The first one is, yes, of course, you have to deliver the right beam shape. This beam shape has to be a rectangular top hat shape to adapt to the fiber shape. the dimensions of this rectangular shape has to be accurate, because you want to hit only the required area, meaning that you want to hit only the fiber that is deposited and not the fibers that are alongside, or even worse, you don't want to hit parts of the machine. Also, the intensity profile of this top hat has to be homogeneous, because while it is homogeneous, you will have a uniform heating over the tape that is deposited, and then enhance the mechanical properties of the final part. But also, in parallel of this, let's say, optical challenge, we also have a design challenge on the compacity of this beam shaping laser head. If you want to be able to drop highly curved parts, you have to have an ultra compact beam shape to reduce the mechanical footprint of the robot arm that is depositing the fiber. Denis will go a bit further on this point later on the presentation. And also, we kept in mind that the beam shaping laser head has to have a reduced width and mass to be integrable in parallel. For example, on the C5 machine that is capable of depositing multiple tapes of fiber in parallel. And then you have to adapt with multiple optics to hit each of the tapes. So now I will present more in detail the beam shaping solution that has been developed at Cailabs. What is this laser head, and what are the optical results? So, as I said in the beginning of the presentation, at Cailabs, we used the multiplane light conversion as a core technology for all of our products. So, a bit of theory. What is MPLC? The MPLC is enabling a free-form beam shaping through the succession of spatial space profiles with a specific propagation distance between themselves. So as you can see on this left picture. The implementation of this beam shaping technology is totally passive, with no electronics, no moving parts, and no intrusive loss. On this picture, on the left-hand side, you can see an implementation in a transmissive way. But at Cailabs, we decided to implement it in a reflective way. Firstly, because it's less bulky, but also it can better handle the high power or high energy of lasers. Also, to finish, multiple beams can be shaped simultaneously. On the right-hand side, you can see a telecom-based implementation of the MPLC with a few single modes entries here to combine all of them, multiplex all of them in only one output. All of this makes the MPLC a good candidate for high power or high energy beam shaping and/or combining. So this is theory. Now in practice, this is the laser head that we have been designing at Cailabs. So you can see an LLKD connector to be able to plug in the laser fiber, and the MPLC beam shaping mirrors. At the back of those beam shaping optics, you can see water cooling. This water cooling by the back of the optics enable a uniform cooling, and then ensure homogeneous optical properties of the optics all over the process. And then you have an optical window to deliver the beam shape free space to the processing plane. Few figures about this laser head that has to be integrated and used in an industrial environment. As I said earlier, the compactness of the system is very important. The weight of the laser head is no more than 1 kilogram, including the connector, which is actually representing about a half of the weight. So you can imagine the performance of our MPLC-based laser head in terms of weight reduction when you know that the LLKD connectors is representing a half of the total weight of the optical system. As I said, it is linked by an LLKG connector, which allows our laser head to be ready to use, plug and play with no optical adjustment. And as an input, there is a diode laser from Laserline, 6 kilowatt maximum power. And also to be able to in process monitor some parameters, we implemented some sensors, for example, PT100 for the temperature of the optics. Now, a few words about the optical performances of our system. Unfortunately, the total dimensions of the rectangular shapes, are confidential, so I won't be able to communicate to communicate them today. But we can still evaluate the performance of our system thanks to relative metrics. For example, we can look at the sharpness of the top hat shape, which is calculated here as the transition length, here LG or LD, divided by the total length, L 10% here, and which is no more than 1/7 here in our case, which is quite good sharpness. The plateau homogeneity of the top hat shape has also been measured and is no bigger than 3% RMS, which is also a very good, a very interesting performance. A few words about now the depth of field of our laser head. So this laser head is designed for a nominal working distance of 240 millimeters. But we conducted different tests at a different working distance from the nominal one. And we can see that the shape is quasi constant at 250 millimeters working distance, or 260, with a growth of the dimensions over the length of 4% and 6% respectively, and of 6% over the width. So this is why I said the growth is quasi constant over this distance. At a wider working distance, 295 millimeters, the growth has been measured as plus 14% and plus 12%, but the shape, meaning we still have, the shape is preserved, meaning we still have a rectangle at this distance. So we can say that we have a shape preserved, so a depth of field of plus or minus 50 millimeters. This depth of field is particularly interesting because it gives a robust process, which is robust, to working distance variation that could be initiated by any reason. A few words now about the power management. We also had to validate the high power handling of our beam shaping laser head. First, on the transitional regime, meaning when we start the process. As you can see on the chart here, the temperature of the optics is stabilized in about 5 minutes after the start of the process, and meaning that our system has a stable operation up to 6 kilowatts. A few words about the transmission of our system that has been measured, and it's bigger than 97%, which is an excellent transmission. And this transmission is the assurance of stability of the process, and to have an increased power efficiency over the optical chain. So to sum up all those results in terms of optics, we are here showing why the MPLC is a particularly suitable answer to the Coriolis composites needs. So first of all, there are interesting advantages of the MPLC technology. First, it could be perceived as simple, but it's the first requirement. The beam shape that you target is the right one that you'll have at the output of the beam shaper. So you have the required beam shape here, a rectangle. The dimensional accuracy is also respected. You also have a high quality in terms of sharpness and homogeneity. And to give you a proof that these advantages are really intrinsic to the MPLC, we organized few months ago a webinar where we benchmarked a diffractive optical element compared to an MPLC beam shaper in a slightly different context for ultra short pulse laser beam shaping. But we demonstrated on the theoretical point of view, on experimental point of view, the intrinsic advantages in terms of quality of the MPLC. If you want to watch this webinar, I think it's available on the Cailabs website, and I really encourage you to go and watch this webinar with, for example, a live demonstration by one of our colleagues with benchmarking in parallel an MPLC Canunda pulse module compared to a diffractive optical element. Okay, that's it for the intrinsic advantages of the MPLC. Now, the reflective implementation of our technology is also giving advantages in answering the Coriolis Composites needs. As I said, the reflective implementation is enabling an efficient power management, bringing stability to the process and high optical energy transmission. And also, the reflective implementation is enabling the design of a laser head with a reduced bulk and mass, and this is making the industrial implementation of the laser head easier and more efficient for Coriolis Composites. And this is exactly what Denis is going to show you now. So Denis, the floor is yours.
Thank you very much. Yeah, now we'll speak about how the CANUNDA-HP has been mounted and used in our C-Solo machine, as you can see on the pictures. So, as Julien said in the introduction, one of the main goals for us to work with Cailabs was to reduce the bulk of the optics. We had a need to put several optics side by side at a pitch of 1.5 inch, which is the standard width for our C5 machines, and we needed to put several optics side by side on the optics we used before, or we used usually, were too wide and we couldn't put them side by side. So we decided to develop that optic in that first game. So one, to put them side by side, so they must be no wider than 1.5 inches, and two, have a reduced volume and weight to be able to manufacture a much more complex part. And you can see that that has been fulfilled fully with a comparison of our previous, or the optics we use on our C-Solo, which I call reference, and then a CANUNDA-HP. Then just a few illustrations of why the volume is important, and you can see here on it's the simulation of the manufacture of a nacelle structure, and you can see there that the part is very complex. And with the AFP, you have to be able to roll. The head has to be able to roll inside the mold to be able to manufacture it. And the large laser optics will augment or increase dramatically the volume, the bulk of the head, so that would limit us in the terms of which parts we can make. So with a CANUNDA-HP optics, we can manufacture much more complex structures, like the one shown here. Then we also had the opportunity to work on the beam shape and beam dimensions to optimize the health of the material. So the main advantage of thermoplastic processing is that if you do it in a conditions which are called in situ, you can manufacture the part, and after the layup, the part is nearly finished, except for a few operations such as trimming or drilling. To do that, you need to have to optimize your process parameters to get a good laminate quality, and using the opportunity of the development of a new optics, we worked on the dimensions of the size of the laser beam, and we can see here on these slides that thanks to that we managed to reduce the porosity content, changing the laser beam shape. And I must say that it's at similar processing conditions, so similar compaction pressures, similar layup speed, and similar layup temperature. We managed to reduce the porosity content by about 30%. So that was very interesting for us too. So Coriolis is very happy with the development of this new optic. So thank you very much.
Thank you, Denis, for those very interesting results. We are also very happy at Cailabs that our technology had been able to answer to your industrial needs and integration needs on your machines. So I think it's the perfect time to sum up what we saw today on this study, and what messages you should take home after this webinar on the study between Cailabs and Coriolis Composites. So first of all, we can say that Cailabs has provided a fully integrated beam shaping laser head that is delivering a rectangular top hat shape, thanks to our core technology, the multiplane light conversion (MPLC). This laser head is about 2 times more compact than the previous solution, as we can see in the earlier in the Denis slide. So we are really happy with that, and also we also provided a high quality beam shaping thanks to the, as I said, intrinsic qualities of the MPLC. Also, the final goal of this study, our laser head has been integrated on the Coriolis composite machines to do process and automated fiber placement has been demonstrated, and has also enabled an improved quality in terms of porosity, as Denis mentioned earlier. Okay, so that's now the time for the second and last survey session of today. So, we would like to know, in your opinion, for what other application than IFP do you think the Cailabs laser head, so CANUNDA-HP top hat shaper, could be suitable? So I remind you, this IFP, laser head is delivering a rectangular top hat beam shape. So maybe it could be used for laser hardening, polishing, cleaning, drying, or maybe also another application. So you can pick one or several answers if you think that our laser head could be suitable for several applications. And if you have an idea of another application, also we will be glad to know it. So I will give you some seconds to make your decisions. So for the moment, some of you think that laser hardening or laser cleaning are particularly suitable applications for our laser head. One people more think that laser cleaning is suitable, is addressable with our laser head. So that's interesting results. So I think now we can go back to the presentation, to the slides. And so actually, all those processes seems to be addressable thanks to our beam shaping solution. So a few words about CANUNDA-HP top pad shaper. So it's a laser head, as I said, which is now available off the shelf. And then you have factory set configurable dimensions of the rectangle. You can choose the length and the width of the rectangle in a factory set configuration. And those dimensions are selectable over a standard range of dimensions. So the next steps for this laser head in other processes than automated fiber placement are process tests for laser hardening or polishing, or even cleaning or drying, as you mentioned in the previous survey. So if you are interested in these processes and to work with Cailabs, on those processes, please do not hesitate to contact us. Now, in parallel, the CANUNDA-HP top pad shaper is also available on the brand new, on the existing, Coriolis Composites machine. Maybe, Denis, could you tell us a bit more about what are the compatible machines?
Yes, of course. So thanks to the connectivity with the optical fibers, the range of CANUNDA-HP top pad shapers are available, can be used on any Coriolis machine, the current ones or the future ones. They've been already tried and tested on the C-Solo machine, and it's kind of pre-designed for the C5 machine, which is a multi-wide toe machine where you have several times 1.5 inch toes, which you need several laser source each time. And obviously for the C1 machine, which has been shown in the simulation, so basically the machine where which is also multi-toe, but 1/4 inch this time, with which is a machine which is used a lot in aeronautical industry for manufacturing complex composite parts. Thank you very much.
Okay, thank you, Denis. So we are reaching the end of the presentation now. So it's time for us to answer to your questions with this Q&A session. So now we will activate the Q&R mode. So we have a question from Guillaume Bouquet. Is there any possibility to customize dimensions of the necessary shape we need with your HP top pad shaper? So I think I gave a part of the answer in the last slide of the presentation. Yes, you can customize the dimensions of your rectangular shape over a standard range of dimensions over length and width. You can also customize the working distance. So we are pretty sure that our standard offer can answer many of the surface treatment laser applications. So I hope I answer your question, Guillaume. Okay, is there? Yes. So Jean-Marc Deco is asking, heating of composites would be more effective with CO2 or blue lasers. So CO2 lasers are emitting around 10 microns wavelength, while blue lasers around 400, 450 nanometers. While CO2 is not suitable for easy robotic handling, blue laser could be interesting and require much less power than 1 micron sources. Is Cailabs considering 450 nanometers as well? So maybe for the first part of the question, I will ask to Denis his advice, because he probably better know than me the interaction between light and composites. Maybe would it be more efficient at 10 microns or at 400 nanometers wavelengths? I don't know. What is your what you think about that, Denis, and I'll be answering on the second part of the question. Yeah, the floor is yours.
Of course, thank you, Julien. Yeah, that's a very good point. That's a very good question. When we started to look at lasers to process thermoplastic materials, we considered different types of lasers. Obviously, well, as you said, the CO2 lasers are difficult to use on robotic systems because it's difficult to bring the energy from the source to the head or to the compaction head, and it's not compatible with optical fibers. So that's for sure. I don't really know blue lasers very well. We didn't try those, so I don't know. But it is a big issue indeed. I would say the transparency of the composite materials with laser wavelengths. So, for example, these systems work very well for carbon composites because then the laser or the light will hit the carbon fiber, which in turn will melt the matrix. It's a bit more complicated with glass fiber composites. Obviously, at these wavelength, the glass is transparent to the light, so it's much more difficult to hit the material. I'm not very familiar with 450 nanometers lasers, so I can't answer the last part of it.
Okay, thank you, Denis, for your answer. And to answer to the second part of the question, is Cailabs considering blue wavelengths as well? So what I can say is that those wavelengths are not addressed in the standard off-the-shelf version of our beam shaping laser head, CANUNDA-HP top hat shaper. But we could definitely study in a custom project. Blue wavelengths would be very interesting to work on that through a project. So yes, we are considering blue wavelengths, but not yet as a standard product. I hope that I answered your question. Okay, we have another question from Matthew Frost. Good afternoon, Denis and Julien. So good afternoon, Matthew. Is the improvement in laminate quality due to the improved spot size? So I guess it's more a question about material and composites quality. So maybe I will let Denis answer on that one.
Yes, of course. Yes, sure, no problem. Thank you, Julien. Hi, Matt. Yes, it is. As I mentioned before, we took the opportunity to try a new spot as we are developing a new head or laser head. We took the opportunity to change the spot size to something which we thought would be better for in situ consolidation. So yes, it is due to the spot size rather than anything else.
Okay, thank you for your answer, Denis. So I don't know if there is any question. I don't think so. We are going back to the slide, and it's time for us to end with this webinar. So it's been a pleasure to present you those exciting results on automated fiber placement process. Please remember that Cailabs can help you on your laser material processing applications. If you want to implement a beam shaping solution, if you want to implement a beam splitting solutions and improve the yield or quality of your laser material processing, please feel free to contact us. Would be happy to help you. If you want to know more about our products, particularly about the CANUNDA-HP top hat shaper, you can visit the Cailabs website. You'll find a brochure for CANUNDA-HP product that is explaining more in detail what is the proposition of this standard product. And last but not least, I would warmly thank Denis from Coriolis Composites First, it's been a pleasure to work with Coriolis Composites in this project, and also it's been a pleasure to share the floor with you today, and to present you those exciting results. Thank you, Denis.
You're very welcome. Thank you for the invitation. It was a pleasure indeed.
Thank you, Denis. Thank you all. Goodbye. Good evening. Bye.
Bye bye.